Good morning, friends. Today we will discuss Gauss-Quadrature integration, that is numerical integration in finite element. So in finite element analysis, we use Gauss-Quadrature integration formula. Now, the process of numerical integration is called quadrature. Process of numerical integration is called quadrature. And you know that integration is basically process of summation. So integration is basically a process of summation. Suppose if we have a curve y equal to fx, say a curve y equal to fx. Now to find area under this curve, we have to use a numerical integration method, because this is a curve, and in order to find out area under this curve, we can make use of numerical integration. That is, by summation we can find out the area under the curve. Suppose this is point A, this is B. So this is f of A and this is f of B, and the distance between them is, say, h. Interval is h. So to find out this area under the curve numerically, we can use trapezoidal formula, we can use Simpson's 1/3 rule, or any other numerical formula can be used, or by subdividing this area into the known areas in the figures for which we can work out the areas, we find out the area under the curve. Now if you want to use the trapezoidal formula, now this area under the curve, by using trapezoidal formula, we know h by 2, that is f of A plus f of B. So by using a trapezoidal formula, so what is h? H is b minus a divided by 2. So this becomes f of A plus f of B. Or we can expand this, b minus a by 2 f of A plus b minus a upon 2 f of B. So this is nothing but, say, this is m1 f of A plus m2 f of B. Here m1 and m2 are equal, so m1 equal to m2 equal to b minus a by 2. So what is this m1 and m2, where m1 and m2 are multipliers or multiplying constant called weights. Now in a similar way, suppose if you want the more accurate area under the curve, then we have to subdivide this into the more number of figures, and then again by using the trapezoidal rule, we can find out more accurate results. Since this is a numerical method and it gives us approximate but acceptable results. Now in Gauss-Quadrature formula, now Gauss, what he has done, so let's see how to calculate the numerical integration by using a Gauss-Quadrature formula.
Suppose let's consider the same curve, say y equal to fx.
y equal to f of x is a curve is a function of a curve. Now in Gauss quadrature formula, so generally at the center we take the vertical axis, and this is the natural coordinate system xi, and this is xi or x is taken, y or eta is taken in this way. Then in order to find out this area, we have to consider different Gaussian points. And the Gauss, he has assigned weights corresponding to these points. Now suppose if you use one point, that Gaussian point, number of point is 1. So limits of integration always varies from -1 to +1. So this is -1 to +1. And then if n is 1, then he has assigned the weight, say multiplier, is equal to 2. If we consider two Gaussian points, then say then these 2 points are to be for more accurate results. Again, we have to consider more number of Gaussian points. So this is -1, this is +1 within the range under the curve. Say this point is 1, this point is 2, and number of Gaussian points are 2, 1 and 2. And the weights assigned to here, that is multipliers equal to 1 and m2 equal to 1. And this is 1 point Gaussian solution, 2 point Gaussian solution. And if you want to consider the 3, suppose if you consider instead of 3, then we have to take the 3 points, 1, 2 and 3. So this is point 1, this is point 2 and this is point 3. Then the weights assigned corresponding, say m1, m2, m3. So this is 5 by 9, this is 8 by 9 and this is 5 by 9. And here the minus root 3, the location is minus root 3 and plus root 3. So the location, so what the Gaussian he did, that he has considered different locations and assigned corresponding weights to find out integration numerically. Then how the integration is calculated by using this method, I equal to, say this is a to b, integration f of x dx. So this is to be converted into this integration -1 to +1 in natural coordinate system. So this is f of, so we have to f of xi to dxi. So that means we have to convert first fx to fxi. Then this is, because integration represents the summation, so this is nothing but summation I equal to 1 to n, this mi weights assigned into fxi I. So this gives us the numerical integration by using Gaussian formula. Now this formula is called the Gaussian formula. Now suppose, that means for 1 point solution, this I becomes, this is simply m1 f xi 1. For 2 point solution, I equal to, so this is m1, not this is m1 f of xi 1 plus m2 f of xi 2. If you take 3 point solution or 3 Gaussian points, then I equal to m1 f of xi 1 plus m2 f of xi 2 plus m3 f of xi 3. And so on. If more number of points are considered, considered, then accordingly this is to be worked out. So that means to calculate the integration, numerical integration by using the Gaussian points, so and how this number of Gaussian points are to be considered, that depends upon the function or polynomial for which we have to calculate the integral. Then the 2n minus 1, say for exact results or accurate results, the number of points are considered equal to 2n minus 3, where n is the number of Gaussian points. So, and depending upon the order of polynomial for which the integration is to be worked out, we can decide how many points are to be used in order to calculate the exact or very close to the exact integration value answer. Now, say by using this formula, Gaussian formula, we can now find out, we can solve some problems. So, say, let's solve the problem I equal to, find integration or evaluate integration for I equal to 3 to 7 f of x dx, where the function fx is equal to 3, see this is, let's take 4x square plus 3x plus 10. So this polynomial has the second order, and from that we can decide the number of Gaussian points to be used to find out the accurate solution. Anyway, this is the simple function. We have fx equal to 4x square plus 3x plus 10, for which we can calculate the exact integration also. And then we can compare this integration with the answers obtained by using the Gaussian integration formula. Now, before to find out the numerical integration of this, let's converge. So first conversion of fx to f psi. And for this conversion, there is one formula that we have to use. X equal to b minus a upon 2 psi plus b plus a upon 2. So you remember this formula, you have to remember, this is linear conversion. So we can convert this fx to f psi by using this relation. Now substitute, so a is the lower limit and b is the upper limit. So limit of integration is 3 to 7. So substitute this 7 minus 3 upon 2 psi plus 7 plus 3 upon 2. Now this is 7 minus 3 is 4 by 2. So this is 2 psi. 7 plus 3, 10 by 2 is 5. So this is 2 psi plus 5. Also we have to find out dx. Dx equal to 2d psi. Differentiating this. So dx is 2d psi. Then what is fx? So fx. So now integration. Let's write down this. I equal to integration 3 to 7 fx dx. So now this becomes integration minus 1 to plus 1. Integration as per the Gaussian integration form. This is minus 1 to plus 1, and this is f of psi d psi. Now let's, dx is nothing but 2d psi. So this is 2d psi. So this becomes 2 integration minus 1 to plus 1 f of xi, say d xi. Now, so this is nothing but summation. So 2 into summation I equal to 1 to n m I f of xi I. So this is Gauss quadrature formula. This is called Gauss quadrature formula. Now depending upon the number of points, we can use this. Now there is a one table, so that table I am giving, the whole table, I will put it on Google Classroom or even Moodle notes. Already it is uploaded on your Moodle, you can see this. Say the table is like this. Number of Gaussian points, say n values, then the weights or location we can take, say m values, weight and location. Say if you take 1 point solution, m is 2 and location that is 0, xi is 0. If you take 2, then you will have this 1, that is m1 equal to 1, m2 equal to 1, and here xi1 is minus, that is 1 upon root 3, and xi2 is minus 1 upon root 3. If you take 3 points, so your m1 is 5 by 9, m2 is 8 by 9, and m3 is again 5 by 9. And xi1 here is minus, or first you may take plus root 0.6, xi2 is 0, and xi3 is minus root 0.6. So these are the, depending upon the number of Gaussian points, so we can take these values, weights and xi. So this table will be given to you. Now here say using 1 point Gaussian solution or simply solution, Gauss point solution. So if we take 1 point, so this is simply m1 f of xi1, but 2 is there in the basic formula, so we'll take this 2 into bracket m1 f of xi1. Now what is m1 and xi1? So if it is 1 point solution, m1 is 2 and xi1 is 0. These values, m1 and xi1. If it is 1 point, m1 is 2, xi1 is 0. Now substituting this 2, m1 is 2. Now we have to work out the xi1 also, f of x. So let's develop this first. F of x equal to f of xi. So this is equal to, what is the equation? 4x square. 4 into x is 2 xi plus 5 bracket square. Then plus 3, x again substitute here, 2 xi plus 5. Then 3x plus 10. So this is 4 into 2 xi square plus 20 xi plus 25 plus 6 xi plus 15 plus 10. So now the equation you just multiplied by this 16 xi square plus this 80 xi plus this 6, 86 xi plus this 100 plus 10 plus 50. So this term now 4 into 25, 100 plus this 25, so 125. So this is 125. Now this is fx. Now using this, what is f of xi1 is equal to, what is xi1? Xi1 is 0. So putting this xi1 0, so what we get is 125. Therefore, I equal to 2 into bracket, m1 is 2 into 125, so the answer is 500. The answer is 500. But we can find out the exact also. Now this is 500. Now let's consider 2-point solution. Let's consider 2-point solution. Now using 2-point Gaussian solution or 2-point Gaussian points, say what is I becomes now 2 into bracket m1 f of xi1 plus m2 f of xi2. Now what is m1? So m1 equal to m2 equal to 1. And what is xi1? Xi1 equal to 1 by root 3 and xi2 equal to minus 1 upon root 3. So xi1 and xi2 are this. Now this point, 2-point solution we are using. Now let's find out first f of xi1 and f of xi2. So f of xi1 now becomes this 60. Xi1 is 1 by 16 into bracket 1 upon root 3 bracket square plus 86 1 by root 3 plus 125. So you will get f of xi1. Similarly, f of xi2 equal to 16 into 1 minus 1 by root 3 bracket square plus 86 minus 1 by root 3 plus 125 equal to. And once we calculate this f of xi1 and xi2, so I equal to 2 into bracket m1 is 1 into this, you write down f of xi1, 1 into f of xi1, this value we can write from here, plus 1 into f of xi2. So this answer is somewhat, I think 521 something point something, that you can work out this answer. And even exact answer also you can work out. And you can compare both 1-point solution, 2-point solution with the exact solution. So how to calculate exact? So we have integration I equal to 3 to 7. So this is 4x square plus 3x plus 10 dx. So let's find out the exact answer. So this is equal to, we know, integration 4x cubed by 3 plus 3x square by 2 plus 10x from 3 to 7. So this upper limit minus lower limit. You can do upper limit minus lower limit and find out this 2, and then you compare this and this answer. And now you will find this 2-point solution and the exact answer, they are approximately same. They are very close to each other. That means we can use the Gauss quadrature formula to calculate numerical integration in finite element by using natural coordinate system. So the further problems, you will be given the problems for practice. So you try to solve them and learn how to calculate the numerical integration in finite element by using the Gauss quadrature formula. So this formula helps to get the numerical integration. You want to work out the element stiffness matrix for any type of element. So the further problems will be given for practice. as an assignment, and you can solve them so that you will have a sufficient practice of evaluating numerical integration using Gauss quadrature formula.